Welcome to the Arduino OOP course. I am thrilled to have you here. In this journey, we are going to transform the way you write code for Arduino, moving from basic scripts to professional, scalable, and reusable object-oriented programs. This course is a step-by-step project-based guide. We won't just talk about theory. We will build a real-world project while mastering OOP concepts like classes, objects, encapsulation, and abstraction, specifically tailored for the Arduino ecosystem. By the end of this course, you will be able to write clean and readable code, package your functionalities into easy-to-use libraries, and handle complex projects by combining multiple objects without the usual headache of spaghetti code. Whether you are a hobbyist looking to organize your projects better, or a developer wanting to apply professional software engineering principles to hardware, this course is designed for you. Let's get started. Coming up next, we'll dive into the big question: why should you use OOP for Arduino? See you in Lecture 01.02. Why OOP for Arduino? You might be used to the traditional functional way of writing code in the Arduino IDE. While that works for small projects, it quickly becomes a mess as your project grows. Today, we will explore why object-oriented programming is a game-changer for hardware development. In procedural programming, you often end up with global variables and long functions. When you want to add a second or third LED, you have to duplicate variables and logic, leading to what we call spaghetti code. With OOP, we treat components like real-world objects. Instead of managing pins and states manually everywhere, we create an LED object that knows how to handle itself. This makes your code reusable, much easier to read, and perfectly scalable for complex robots or IoT systems. As you can see in this comparison, while procedural is fine for a blinking light, OOP is the professional standard for anything more advanced. It separates the how it works from the what it does. Now that you know the why, let's prepare for the how. In the next lecture, 01.03, we will go through the list of materials you need for this course. To follow along with the hands-on projects in this course, you will need a few hardware components. Don't worry if you don't have everything right now, as we will start with simple setups and gradually build up to our final project. First and foremost, you need an Arduino board. I recommend the Arduino Uno as it is the most standard choice, but any Arduino-compatible board like the Nano or Mega will work perfectly fine for these OOP concepts. For our specific projects, please gather 3 LEDs, ideally red, green, and yellow for the traffic light system along with matching resistors. You will also need 2 push buttons for digital input and 1 potentiometer to practice analog data handling within our classes. And of course, ensure you have a USB cable to connect your Arduino to your computer for uploading the OOP code we are about to write. Once you have your hardware ready, we need to prepare our workspace. In the next lecture, 01.04, we will look at the software setup required for the course. See you there. Before we start coding our classes, we need to ensure our environment is ready. Modern Arduino development can be done in several ways, but for this course, we will focus on the tools that best support object-oriented programming structures. I highly recommend using the Arduino IDE version 2.0 or higher. It provides better code completion and navigation, which is incredibly helpful when working with multiple files and classes. You can download it from the official Arduino website for Windows, macOS, or Linux. The installation is straightforward. Once installed, make sure you have the AVR board's core updated. The Arduino AVR boards may be installed automatically when you open Arduino IDE. If you are an advanced user, you can also use Visual Studio Code with the Arduino extension, which offers even more powerful tools for managing large OOP libraries. If you see the Remove button like this, you have installed completely. If you use macOS, maybe you need to install additionally Xcode command line tools. If you have been a software developer for a long time, maybe your Mac has been installed. Here is a way to install. First you choose this board. Then you click on this Verify button here. Then you will see this one. To upload, you connect the board to the Mac. Then you click on Select Board. You will see an option like this. You choose it. Now you try to upload by clicking on this button. Throughout this course, we will be creating our own libraries. Ensure you know where your Arduino/libraries folder is located on your computer, as we will be moving our custom OOP classes there in later sections. With the hardware and software ready, it's time to see the big picture. In the next lecture, 01.05, we'll go through the project overview and I'll share tips on how to get the most out of this course. In this final lecture of the introduction, we will look at the road ahead. Understanding the big picture will help you stay motivated and see exactly how each individual concept fits into the final complex system we are going to build. Our primary goal is a complete traffic light system. We will start simple by creating an LED class, then a push button class. As we progress, we will learn how to make these objects talk to each other and eventually use a state machine to control the entire sequence smoothly. To truly master OOP, don't just watch the videos. Type the code along with me. When we finish a class, try to add a new method or change an attribute. Experimentation is the best teacher in programming. By the time we reach the end, you won't just have a traffic light. You will have a library of reusable components that you can drop into any future Arduino project, saving you hours of coding time. The introduction is over. It's time to get our hands dirty. In the next section, Lecture 02.01, we start building your very first Arduino class. See you there. Welcome to Section 2. It is time to move from theory to practice. In this section, we are going to build your very first Arduino class from scratch. We will use a simple LED as our subject, which is the perfect way to understand the core building blocks of object-oriented programming. An LED might seem simple, but it has everything we need to learn OOP. It has properties like a pin number and a state. and it has behaviors like turning on, turning off, or blinking. By the end of this section, you will start thinking about digital right and start thinking about LED objects. We will follow a structured path, first defining the blueprint, adding their attributes, setting up the constructor, and finally creating methods to control the hardware. This modular approach is exactly how professional libraries are built. Instead of having variables scattered at the top of your sketch, all the logic for the LED will be contained within the class. This makes your main program incredibly clean and easy to manage, especially when we add more LEDs later on. Are you ready to write your first line of OOP code?
Let's go.
In the next lecture, 02.02, we will create the basic structure of our LED class. See you there. In this lecture, we are going to lay the foundation. We will create the basic shell, or the blueprint, of our LED class. In C++, which is the language Arduino uses, a class is defined using the class keyword followed by the name of the class. To define a class, we use the keyword class followed by the name, in our case, LED. By convention, class names start with an uppercase letter. We then open a pair of curly braces and, very importantly, we must end with a semicolon after the closing brace. Inside the class, we need to decide who can see our data and functions. We use access specifiers like public and private. For now, we will add the public keyword because we want our main program to be able to interact with the methods we'll create later. Think of this code as a blueprint for a house. It defines how the house should be built, but it is not the house itself. Right now, our class is empty, but it's the container that will hold all our LEDs, properties, and behaviors. Now that we have the shell, let's give it some characteristics. In the next lecture, 02.03, we will add attributes to the LED class. See you there. Now that we have our class structure, it's time to add attributes. Attributes are the data, or variables that belong to the class. For an LED, what information do we need to keep track of? Primarily, a digital pin it's connected to and its current state. We will add two variables. A byte named pin to store the hardware pin number, and a byte named state to remember if the LED is currently high or low. Note that we place these under the private access specifier because we want to protect this data from being changed directly by the main program. This is a core concept called encapsulation. By making these attributes private, we ensure that the state of our hardware remains consistent. The only way to change the LED state will be through the controlled methods we'll write later. In Arduino development, we use lowercase for simple attributes. Some developers like to add an underscore prefix to private variables, like underscore pin, to distinguish them from local variables. Choose a style that works for you and stay consistent. We have the data, but how do we initialize it? In the next lecture, 02.04, we will create the constructor, which is the function that runs when you create a new LED object. See you there. The constructor is a special function that is automatically called when you create an object. Its job is to initialize the attributes of the class. In our case, The constructor will take the pin number as an input and set up the hardware for us. A constructor must have the exact same name as the class, and it does not have a return type, not even void. We place it in the public section, so it can be called when we create an instance of the LED. Here, we pass a byte name pin as an argument. Inside the constructor, we assign the incoming pin value to our private pin attribute using the this pointer to avoid confusion. Then, we do something very important. We call pin mode to set our pin as an output. Now, the object is ready to control the hardware the moment it is created. By putting the pin mode logic here, we ensure that every LED object we create is automatically configured correctly. We also set a default state of LOW to make sure the LED starts in the off position. Our LED class can now store data and initialize itself, but it still can't do anything. In the next lecture, 02.05, we will add methods to actually control the light. See you there. Methods are the functions that live inside a class. They define the behaviors of our object. For our LED class, we want to be able to turn the light on, turn it off, and maybe even toggle its state. Let's write the logic to make this happen. We will add two simple methods, on and off. Inside on, we set our state variable to high and call digital write using the pin attribute. The off method does the exact opposite. Notice how these methods are public, so they can be called from our main loop. A very useful behavior is toggle. Instead of checking if the LED is on or off ourselves, we let the object handle it. If the current state is high, we call off, otherwise we call on. This abstraction makes our main code much cleaner. By using these methods, we ensure that the internal state variable always matches the actual hardware. You no longer need to remember which pin is connected to which LED. In your main loop, you just tell the object what to do. Our blueprint is complete. Now, let's see it in action. In the next lecture, 02.06, we will instantiate an LED object and run it on a real Arduino. See you there. It is finally time to bring our code to life. We have the blueprint, but now we need to create an actual object from it. In this lecture, we will learn how to instantiate our LED class and use it to control a real LED in our Arduino program. To create an object, we use the class name followed by our chosen object name. Here, we create an LED object named myLED and pass the value 13 to the constructor. This tells the object it is connected to pin 13. We do this at the top of our script, outside any functions. Now, look how clean our loop becomes. We simply call myLED.on, wait for 500 milliseconds, then call myLED.op. We don't have to worry about the pin number or the digital write command anymore. The object handles everything internally. The real magic happens when you need more components. You can create a red LED and a blue LED just by making new instances. Each one will manage its own pin and state independently, keeping your main sketch clean and professional. Congratulations on creating your first Arduino class. But having the class inside your main sketch can get messy. In the next section, Lecture 03.01, we'll learn how to organize our code by moving the class into separate files. See you there. Welcome to Section 3. While having our class inside the main Arduino sketch works, it's not very professional. As your projects grow, your main file will become cluttered and hard to navigate. In this section, we will learn how to organize our classes like professional developers. Right now, if you want to use your lead class in a different project, you have to copy and paste the entire class code. This is inefficient and makes updating your code a nightmare. We need a way to make our classes truly portable. We are going to split our code into 3 distinct files. The header file tells other parts of your program what the class can do, while the CPP file contains the actual code for how it works. Your main sketch will then stay clean and focused only on the high-level logic. We will start by creating the header file, move our logic to a source file, and finally, I will show you how to turn your code into an official Arduino library that you can use across all your future projects with just a simple include line. Ready to clean up your workspace? In the next lecture, 03.02, we will begin by creating the header file for our lead class. See you there. In this lecture, we start our organization journey by creating the header file. Think of the header file as the interface or the menu of your class. It tells the compiler and other developers what your class can do, without showing how it actually does it. A header file usually has a .h extension. Its primary job is to hold the class definition, including the attributes and the function prototypes. It acts as a contract between your class and the rest of your program. To create a new H file in Project folder, first you need to click on this button. Then you click on New tab. You name new file like me here, and click on OK. Now we are here. Whenever you create a header file, you must use header guards. These preprocessor directives if def, define, and in diff prevent the compiler from including the same file twice, which would cause errors. It's like a safety lock for your code. Inside lead.h, we define our class. Notice that we only provide the function names and parameters here, followed by a semicolon. We don't write the actual logic yet. That's the job for the source file. Now that we have our interface defined in the header file, let's write the actual logic. In the next lecture, 03.03, we will create the CPP file to implement our methods. See you there. Now that we have our header file acting as the interface, it's time to build the engine. In this lecture, we will create the .cpp file, also known as the source file. This is where the actual logic for our lead class will live, keeping the implementation details hidden away from the main sketch. First, we create a new file named lead.cpp. The very first thing we must do is include our header file. By using double quotes instead of angle brackets, we tell the compiler to look for the file in our local project folder. To tell the compiler that these functions belong to our lead class, we use the class name followed by 2 colons. This is called the scope resolution operator. Without it, the compiler would think these are just regular global functions. We then complete the rest of our methods, of and turtle. Notice how the logic is exactly the same as before, but it is now neatly tucked away in its own file. This makes our project much more modular and professional. We have successfully separated the interface from the implementation. In the next lecture, 03.04, we will recap this structure and I will show you how to read and use these files effectively. See you there. Great job! Now that we've split our code, let's take a moment to recap. Understanding how to read the interface is key to using classes created by other developers. You don't need to know how the engine works to drive the car. You just need to know how to use the steering wheel and pedals. Remember, the .h file is the interface that lists the methods available to you. The .cpp file is the implementation. It contains the logic. As a user of a class, you'll spend most of your time looking at the header file to see what commands you can call. To use our organized class in the main sketch, we simply include lead.h at the top. This tells the compiler about the lead class. From there, we use it exactly like we did before. Notice how clean our main file remains, no bulky class definitions getting in the way. When you download a new library, the first thing you should do is open the .h file. Ignore the private section and look straight at the public methods. This tells you exactly how to interact with the component. It's the ultimate documentation for your code. You've mastered project organization. But what if you want to use this lead class in every project without copying files? In the next lecture, 03.05, we'll turn this into an Arduino library. See you there. In this final lecture of Section 3, we are going to take your organization to the professional level. We will turn our lead class into an Arduino library. This allows you to use your code in any future project just like you use the built-in libraries, like Wire or Servo. To create a library, you need to navigate to your Arduino libraries folder. Create a new folder named leadlib, and move your lead.h and lead.cpp files there. This centralizes your code so all your sketches can access it. In Mac you can find the Arduino folder by opening the Documents folder. If you don't know how to open the Documents folder, you open the Finder, then you follow this image. Every library needs a metadata file called library.properties. This file contains information like the library name, version, and author. It's what the Arduino IDE uses to display your library in the Library Manager. Now, in any new sketch, you don't need to copy files anymore. Simply use the angle brackets with the include directive. Your lead class is now a permanent part of your development toolkit, ready to be reused in any project you imagine. You've officially leveled up your coding structure. Now that our software is professional, we need the hardware to match. In the next section, Lecture 04.01, we will build the physical circuit for the course step by step. See you there. It's time to build the physical foundation for our course. In this lecture, we will assemble the complete circuit that we'll use throughout the remaining sections. We'll connect our LEDs, buttons, and a potentiometer to the breadboard, ensuring everything is wired correctly for our OOP objects to control. First, place the red, yellow, and green LEDs on the breadboard. Connect the long light of each LED to pins 12, 11, and 10 respectively through a 220 ohm resistor. Connect all the short legs to the common ground rail. Next, let's add 2 push buttons to pins 2 and 3. We will use the internal pull-up resistors later in code, so just connect one side to the pin and the other to ground. Finally, connect the hour pins of the potentiometer to 5 volts and ground, and the middle wiper pin to analog input as 0. Double check all your connections. Ensure there are no short circuits and that every component has a solid path to ground. Having a clean circuit now will save us a lot of troubleshooting time once we start writing more complex classes. With the hardware ready, it's your turn to apply what you've learned. In the next section, Lecture 05.01, we'll start building the push-button class. I'll see you there. Welcome to Section 5. Now that you've seen how we built the LED class, it's your turn to take the lead. We are going to apply the exact same professional workflow to create push-button class. This will handle everything from basic reading to advanced features like internal pull-ups and debouncing. Buttons might seem simple, but handling them correctly involves managing states, pull-up resistors, and electrical noise. By encapsulating this into a class, we can create multiple button objects that handle their own complexity, leaving our main logic clean and readable. Our journey will follow the same professional structure we learned before. We'll start with the header interface, move to the implementation, and then add layers of abstraction to solve real-world hardware issues like contact bounds. This is where OP really starts to show its power. Throughout this section, I encourage you to pause and try to write the code yourself before I reveal the solution. This is your turn to think like an object-oriented programmer. We'll use the circuit we just built, focusing on the buttons connected to pins 2 and 3. Ready to get started. In the next lecture, 05.02, we will begin by defining our push-button interface in the header file. See you there. It's time to draft the blueprint for our push-button class. Just like we did with the LED, we start with the header file. This file will define the interface, letting the rest of our program know what a push-button object is and what it can do, without worrying about the internal wiring just yet. We start by setting up our header cards using the if and def and define directives. This ensures our library doesn't get included multiple times by mistake. We also include Arduino.h, so we have access to standard types like byte and functions like digital read. Inside the class, we define our private attribute, the pin number. In the public section, we create the construct prototype which takes a pin as an argument. We also add a method called read that will return the current state of the button. This is the simplest version of our interface. Looking at this UML diagram, you can see the clear separation. The pin is hidden away, while the constructor and the read method are available for the world to use. This clean interface is what makes our main program easy to manage. The interface is ready. Now let's make it actually work. In the next lecture, 05.03, we will create the CPP file and implement the logic for our push button class. See you there. Interface defined, now let's build the implementation. In this lecture, we will create the .cpp file for our push button class. We'll write the logic that tells the Arduino how to initialize the pin and how to actually read the electrical state of the button. We start our push button.cpp file by including the header file we just created. This links our implementation to our blueprint. Remember to use double quotes because this file is part of our local project. Next, we implement the constructor. We use push button : push button to tell the compiler this function belongs to our class. Inside, we store the pin number and set the pin mode to input. This ensures the hardware is ready the moment we create the object. Finally, we implement the read method. It returns a byte, which is the result of the digital read function on our private pin. This encapsulates the standard Arduino function inside our object-oriented structure. Now, the user of the class doesn't even need to remember which pin the button is on. The logic is simple but effective. By separating these into a source file, we keep our project modular. If we ever need to change how we read a button, for example, if we move to a different hardware platform, we only need to update this one file. We've built the engine, now let's take it for a test drive. In the next lecture, 05.04, we will create our first push button object and use it to read a button state in a real program. See you there. The blueprint is ready, and the logic is written. Now, it's time to bring our object to life. In this lecture, we will instantiate push button object in our main sketch and use it to read the physical state of the button on our breadboard. In our main ino file, we first include our push button header. Then, we create an instance of our class. We'll call it myButton and connect it to pin 2. Remember, the constructor we wrote earlier handles the pin mode set for us automatically. Now, in the loop, we call the read method of our object. We don't need to pass the pin number anymore because the object already knows it. We'll store the result in a variable and print it to the serial monitor. This is the beauty of encapsulation. The main loop stays clean. When you run this, you might notice the values are a bit unstable if you aren't using an external resistor. That's because the pin is currently floating. This leads us to our next big challenge: handling different resistor configurations inside our class. We have a working object, but it's not very robust yet. In the next lecture, 05.05, we will upgrade our class to handle internal pull-up and pull-down resistors, making our hardware setup much simpler. See you there. In our previous lecture, we noticed that our floating pin can cause unpredictable readings. To fix this, we usually need resistors. But did you know the Arduino has internal resistors we can control with code? In this lecture, we will upgrade our push-button class to support different resistor modes, making our hardware setup cleaner and more reliable. When we use a pull-up resistor, the pin is connected to 5V by default, reading high. When the button is pressed, it connects to ground, reading LOW. Our class needs to know which mode we are using, so it can initialize the pin correctly. We will update our constructor to accept a second parameter, the mode. We'll use the standard Arduino constants like input or input pull-up. We also add a private variable to store this mode for later use. In the CPP file, we update the constructor to apply the specific mode to the pin mode function. Now, if you pass input pull-up, the Arduino activates its internal resistor automatically. This removes the need for external resistors on your breadboard, simplifying your circuit significantly. By handling this inside the class, your main code doesn't have to worry about the wiring configuration. You just tell the object how it's connected, and it takes care of the rest. This makes your code much more portable across different hardware setups. Our button is now electrically stable, but reading high and LOW is still a bit low level. In the next lecture, 05-06, we will add more abstraction to ask our button a simple question. Are you pressed? See you there. Right now, our class returns high or LOW. But as a developer, you don't really care about the voltage. You care about the action. Is the button pressed or not? In this lecture, we will add a layer of abstraction that translates these electrical signals into a simple true or false answer, regardless of whether you are using pull-up or pull-down logic. Abstraction means hiding the messy details. If we use input pull-up, a pressed button actually reads low. That's confusing to read in a main program. We want a method that simply returns true when the button is pushed, handling that inversion internally. We add a new public method called isPressed. It returns a Boolean. This is the only method the user will need to call most of the time. Notice how our interface is becoming more human-readable and less about electronic pins. In the implementation, we check the mode. If the mode is input pull-up, we return true. If the reading is LOW. If it's a standard input, we return true if the reading is high. This internal logic ensures that isPressed always means exactly what it says. Look how much cleaner our loop becomes. No more comparing against high or low. We just ask the button if it's pressed. This is professional-grade code that is easy to read, easy to debug, and easy to maintain. Our logic is now human-friendly. However, mechanical buttons have a hidden floor call bounce that can trigger our isPressed method multiple times in a millisecond. In the next lecture, 05-07, we will solve this by adding debouncing directly inside our class. See you there.
Welcome back.
While our push button works, hardware buttons have a physical floor call bouncing. When you press them, the metal contacts bounce rapidly, causing the Arduino to see multiple presses in many milliseconds. Today, we will fix this by implementing a debounce mechanism directly inside our class. In the header file, we add 4 new private members. About the delay, this is the debounce time. The purpose is that when you press a mechanical button, the internal metal contacts don't close perfectly. They bounce or vibrate, creating a rapid sequence of high, low signals for many milliseconds. About the state, this stores the last stable logic state of the button. Purpose, it serves as a reference to compare against the instantaneous value from digital read. If the current reading differs from state, it means a potential change has occurred. Next is ignore until. This is the LARCAP timestamp. Purpose, it records the exact point in time when the program is allowed to start caring about button state changes again. Finally, underscore has changed. This is a status flag. Purpose, it marks that the button state has just flipped from high to low or vice versa. And in this class we have a new method called hasChanged. In the constructor, we initialize these values. Delay equals 100, means sets the default debounce delay interval. A value of 100 milliseconds is quite conservative and very safe to stabilize our signal. State equals blah blah. This line is crucial for defining the idle state rest state of the button. If using input pull-up, the microcontroller uses an internal pull-up resistor, so the pin sits at high when the button is not pressed. If using input typically with an external pull-down, the pin sits at low when at rest. Ignore until equals 0, initializes the LARCAP timestamp to 0. This ensures that as soon as the program starts running, the button is ready to be read immediately without waiting for any pre-existing delay periods. Underscore has changed equals false, sets the change flag to its default no change yet state. About if ignore until is greater than millis. If the current time millis is still less than the ignore until timestamp, a function skips the logic below. This means that while the button is physically vibrating bouncing, the microcontroller ignores the pin, effectively filtering out the noise about else if digital read pin different from state. Once the silent has passed, the function checks if the actual physical value on the pin digital read differs from the last stable state. If they are the same, do nothing. If they are different, that means a valid press or release event has just been detected. When a change is detected, 3 things happen. Ignore until equals millis plus delay. It sets a new LARCAP timestamp for the future, the next 100 milliseconds. During this time, any subsequent mechanical vibrations will be ignored. State equals not state. It toggles the current state from high to low or vice versa to record the new stable condition. Underscore has changed equals true. It flags that a change has occurred. Note, the condition statement, maybe ignore until greater than millis, will work incorrectly, because maybe millis will come back to 0 in the future. We also implement hasChanged. This method returns true only once per state change. After it's called, it resets the internal flag to false. Constant boolean pressed equals mode is equals to input pull-up $low: high. This line makes our code flexible. If you use input pull-up, the button is wired to ground, so when pressed, the pin receives a low signal. If you use input with an external pull-down resistor, when pressed, the pin receives a high signal. The constant pressed automatically adapts to your hardware configuration. In the next lecture, 05.08, we will combine our LED and button objects to create a responsive system. See you there. In this lecture, we are going to see the real power of object-oriented programming. We have our LED class and our push-button class. Now, we will combine them to work with multiple objects simultaneously. This is where your code starts to look less like a script and more like a professional system. First, we include both header files. Then, we create two LED objects on pins 12 and 10, and two push-button objects on pins 2 and 3. Notice how clean the global scope is. We aren't defining pins or states manually. We are just creating objects. In the loop, the logic becomes incredibly readable. We tell button 1 to check its state, and if it is pressed, we tell the red LED to toggle. We do the same for button 2 and the green LED. Because each object handles its own debouncing and hardware pins, they don't interfere with each other. Imagine doing this the procedural way with global variables, complex if statements. Here, if you want a third LED and a third button, you just add 2 more lines of code. Your main program structure never gets more complicated, no matter how many components you add. Congratulations! You have successfully built and combined your own classes. But we can take this even further. In the next section, we'll learn about composition. Coming up in lecture 06.01, we'll introduce the LED blinker class, where we use a class inside another class. See you there. Welcome to section 6. Until now, we have created independent classes for our components. But what if we want to create a more advanced version of an existing class? In this section, we will learn about inheritance, a core OOP pillar that allows us to create an LED blinker by extending our original LED class. Inheritance creates and is a relationship. An LED blinker is an LED, but with extra features. Instead of rewriting the code to control the hardware pins, our new class will inherit those abilities from the original LED class. This promotes code reuse and keeps our project organized. In C++, we call the original class the base class and the new one the derived class. As you can see, the LED blinker will have everything the LED has, plus new attributes like interval and previous millis to handle timing without blocking the execution. We won't just use the LED methods, we will override them. For example, when we call on a blinker, it needs to start the blinking timer, not just turn the light on. We will also add a setrate method to change speed, and an optic method to keep the timing engine running. Inheritance is a game changer for scaling your Arduino projects. Let's start building it. In the next lecture, 06.02, we will create a LED blinker class structure and learn how to initialize the parent class. See you there. It is time to get our hands dirty with code. In this lecture, we will create the shell of our LED blinker class and learn a crucial C++ technique: how to initialize parent class from a child class. This ensures our hardware is set up correctly before we add our custom blinking logic. In our header file, we use the colon syntax followed by the public keyword and the name of our base class, LED. This tells the compiler that LED blinker inherits everything from LED. Inside, we add our new private variables for timing and state tracking. This part is very important. In the constructor, we use a member initializer list that is the colon followed by the parent class name LED. We pass the pin argument directly to the parent. This is necessary because the parent LED class needs that pin to set the pin mode and initial state. By delegating the hardware setup to the base class, we avoid code duplication. The base class handles the pins, while the derived class focuses solely on initializing the timing variables for its new features. Our structure is ready, and the parent is initialized. Now, we need to decide how our blinker reacts when we try to turn it on or off. Coming up next in lecture 06.03, we will learn how to toggle the LED state from within the LED blinker class. See you there. In this lecture, we will implement the control methods for our LED blinker. Because we are using inheritance, we need to decide how the on, off, and toggle methods should behave. We aren't just turning a pin high or low anymore. We are managing the blinking state of our object. When we call on, we want the LED to start blinking. So, we set is blinking to true and then call the parent on method from the LED class to physically turn the light on. Conversely, off sets is blinking to false and calls the parent off method. To override, you need to put virtual keyword like this in front of the method you want to override in base class. Next, you need to put an override keyword in back of method like this. The toggle method now manages the blinking behavior rather than just the pin state. If the LED is currently blinking, call in toggle will turn it off. If it is not blinking, it will call our new on method to start the blinking sequence. In toggle method definition for LED class, you must add LED : at these two positions. That means you tell the program you need to implement on method of LED class and off method of LED class, not anything else. By using the LED : syntax, we tell the compiler to use the original hardware logic from our base class. This allows us to add our blinking logic on top of the existing hardware control without rewriting the pin management code. We have the controls in place, but our LED isn't actually blinking yet. In the next lecture, 06.04, we will implement the non-blocking timing logic inside the update method to bring our blinker to life. See you there. In this lecture, we are going to implement the heart of our LED blinker class, the update method. This is where we make the LED blink without using the delay function, allowing our Arduino to handle multiple tasks at the same time. This is the ultimate goal of creating a specialized blinker class. The logic follows the blink without delay pattern. We check if the difference between the current time and the last time we toggled the LED is greater than or equal to our defined interval. If it is time to switch the LED state and update our timestamp. Inside LED blinker.cpp, we define the update method. First, we check there is blinking flag. If it is false, we return immediately to save processing power. If it is true, we perform our timing check using millis. When the interval expires, we call the parent's toggle method to change the light state. To make this work, you must call the update method inside the main Arduino loop. Because our logic is non-blocking, the loop can run thousands of times per second. and our LED objects will only toggle precisely when their individual intervals are reached. By putting the timing logic inside the class, we've created a component that is clean. It manages its own time and state, leaving your main program free to handle user inputs or senses without more mess. Our blinker is now fully functional. But what if we want to change the blinking speed while the program is running? In the next lecture, 06-05, we will add getters and setters to control our objects dynamically. See you there. Now that our LED blinker is working, we need a way to interact with its internal settings safely. In this lecture, we will implement getters and setters. These methods allow us to modify the blinking interval, or check the current status of the object from outside the class while keeping our data protected. In OOP, we keep attributes private to prevent external code from accidentally breaking our logic. For example, we don't want another part of the program to set a negative interval. By using a setter method, we can control how the interval is updated and ensure it remains valid. You can get the data of attributes with another type of returning value by using getters. We will focus on the setRate method. This method takes an unsigned long as an argument and assigns it to our private interval variable. This allows us to change the blinking speed dynamically, perhaps based on a sensor reading or a user command, without needing to recreate the object. Here, I don't change anything, just return its original value. In the header file, we ensure setRate and getRate are listed under the public section. This makes them part of our class interface. Other developers, or even your future self, can now see exactly how to interact with the timing of the blinker without needing to understand the internal millis logic. This pattern is called encapsulation. It makes your code more robust because it creates a clear boundary between how the object works and how you use it. You can change the internal implementation later, and as long as the setter name stays the same, your main program won't break. We have built a fully customizable, intelligent LED component. Now it is time to see it in action at scale. In the next lecture, 06-06, we will create an application example where we make 3 different LEDs blink at 3 different rates simultaneously. See you there. In this final lecture of the section, we are going to see our hard work pay off. We will use the LED blinker class to create 3 different objects, each controlling a physical LED at a completely different rate. You will see how easy it is to scale your project once you have a solid class structure. First, we include our LED blinker header. Then, we instantiate 3 objects, red, yellow, and green. We assign them to pins 12, 11, and 10. In setup, we use our setter method, setRate, to give each LED a unique speed, 100 milliseconds for fast, 500 for medium, and 1 second for slow. Look at the loop function. All we need to do is call the update method for each object. We don't need any complex global variables or nested if statements here. Each object independently tracks its own time and state, ensuring they all blink at their designated rates without blocking each other. By using inheritance and the update pattern, we've moved the complexity out of the main sketch and into the class. This makes our code much easier to read and maintain. If you wanted to add 10 more LEDs, you would simply follow the same pattern without making the loop any more complicated. You've mastered the LED blinker and the power of inheritance. Now it is time to face the final challenge of this course. In the next section, we will build a complete traffic light system. Coming up in Lecture 07.01, we'll dive into the final project overview. I will see you there. Welcome to the final section of the course. You have come a long way from creating a simple LED class to mastering inheritance and non-blotting Tina. Now, it is time to put all those pieces together to build our capstone project, a traffic light system. This project is designed to challenge your OOP skills and show you how to structure complex real-world logic. This is the edited final circuit. We aren't just making LEDs flash. We are building a modular system. We will create a traffic light class that manages 3 LEDs and transitions between states: red, green, and yellow. We will also integrate a potentiometer to control the brightness of the LEDs in real time using pulse width modulation, all while keeping our code clean and object-oriented. The biggest challenge here is the state machine. Instead of using a giant switch case in your main loop, the traffic light object itself will decide when to switch from green to yellow based on its own internal timer. This is the ultimate example of encapsulation. Our architecture will look like this. The main loop will simply tell the traffic light to update and the potentiometer to read its value. The traffic light class will act as a manager for our LED objects, and the potentiometer class will provide the data needed to adjust the brightness levels. It is clean, scalable, and professional. Are you ready to build something impressive? Let's get started. In the next lecture, 07.02, we will define the interface and set up the main program structure to kick off our project. I will see you there. In this lecture, we will set up the foundation for our final project. Before we dive into the internal logic of the traffic light class, we need to define how our main program will interact with it. We'll start by defining the interface and the high-level structure of our Arduino sketch. Our traffic light class needs to be easy to use. The constructor will take 3 pins for red, yellow, and green. We also need a public update method that accepts a brightness value. This allows our main loop to drive the logic without knowing about the internal state machine. In our main.ino file, we include the necessary headers and instantiate our objects. We create a traffic light object on pins 11, 10, and 9, and a potentiometer on analog pin 0. This high-level view shows exactly what components our system uses. The loop function remains incredibly simple. We fetch the current brightness from the potentiometer and pass it to the traffic light's update method. This demonstrates the manager pattern. The main loop coordinates the flow of data between independent objects. By defining the interface first, we create a contract. As long as the update method exists and takes a brightness value, we can change the internal logic of the traffic light later without ever touching our main loop code again. With the main structure ready, it is time to build the engine. In the next lecture, 07.03, we will dive into the header and implementation to set up the traffic light class and its internal LED components. See you there. Now that we have our main program structure, it's time to build the traffic light class itself. In this lecture, we will set up the class definition and see how to use composition by including 3 LED objects inside our traffic light class. This is where we define the physical components of our system. In our header file, we first include LED.h. Inside the private section, we declare 3 LED objects: red LED, yellow LED, and green LED. This is called composition. Our traffic light has 3 LEDs. We also prepare an enumeration for our states and variables for timing, which we will use later. In the CPP file, we use the member initializer list to set up our LED object. Because the LED class requires a pin in its constructor, we must pass the R pin, Y pin, and G pin here. We also set the initial state to red and capture the storing time using millis. Why use composition? By embedding LED objects inside the traffic light, we encapsulate all the hardware details. The traffic light class acts as a high-level manager, telling the individual LED objects when to turn on or off without needing to know which pins they are connected to. Our traffic light now has its LEDs ready. But a traffic light isn't very useful if it can't switch colors. Coming up next in lecture 07.04, we will add the methods to initialize and toggle between our red, yellow, and green LEDs. See you there. With our LED objects successfully initialized through composition, we now need a way to manage them as a group. In this lecture, we will implement a utility method to turn all LEDs off at once. This is a critical step for ensuring that only one light is active at a time during state transitions. In a traffic light, we must ensure we never have 2 conflicting lights on at the same time. The set all off method serves as a reset for our hardware. It simply calls the off method for each of our private LED objects: red, yellow, and green. Notice how we are interacting with the LEDs. Even though traffic light doesn't inherit from the LED class, it owns them. When we want to change a light, we send a command to that specific object. This allows us to use the PWM based on method from our LED class to support variable brightness later on. By calling set all off before switching to a new state, we guarantee a clean slate. We now have the ability to control the physical lights, but who decides when they should change? In the next lecture, 07.05, we will implement a state machine to automate the logic and handle the sequence from green to yellow to red. See you there. In this lecture, we will implement the brain of our traffic light, the state machine. Instead of using messy if statements, a state machine allows our object to clearly define which state it is in red, green, or yellow and handle the transitions between them professionally. To make our code readable, we use an enumeration. In the header file, we define traffic state with 3 values: red, green, and yellow. We then create a private variable called current state to keep track of which light is active. Inside our update method, we use a switch statement on current state. This structure ensures that the Arduino only executes the logic relevant to the active color. If the state is red, it only runs the red logic, ignoring green and yellow until the state officially changes. A state machine is all about transitions. Right now, our lights are on, but they don't change yet. By using this pattern, we have prepared the ground to add timing logic next. When one timer finishes, we simply update the current state variable, and the switch case handles the rest automatically. Our state machine is set up and ready to drive the logic. But a traffic light needs to know how long to stay in each state. In the next lecture, 07.06, we will implement time functionalities to handle the waiting periods between states. See you there. Our state machine is set up, but currently, it doesn't know when to move from one color to the next. In this lecture, we will implement the timing logic. We'll use the non-larking millis function to ensure our traffic light stays on each color for a specific duration before automatically transitioning to the next phase. In the header file, we define constants for our durations. We'll set red and green for 5 seconds each, and yellow for 2 seconds. We also use the last change time variable to track exactly when the state last switched. Inside the update method, we compare the current time with last change time. If the elapsed time exceeds our duration, we perform 3 steps. First, turn off the current LED. Second, switch the state variable to the next color. And third, update last change time to the current time. The same logic applies to all states. When green finished, it switches to yellow. When yellow finishes, it loops back to red. Because we use millis, the Arduino is never stuck waiting, allowing it to perform other tasks like reading sensors simultaneously. Our traffic light is now fully automated. It cycles through the colors perfectly. But to make it truly interactive, we need a way to control its brightness. In the next lecture, 07.07, we will create a dedicated class for the potentiometer to handle our analog input. See you there. In this lecture, we will wrap up our hardware components by creating a dedicated class for the potentiometer. Instead of calling analog read directly in our main code, we will encapsulate that logic into an object that can provide us with refined data, such as a map brightness value ready for our LEDs. The header is very straightforward. We store the analog pin as a private member. For the public interface, we have the constructor and 2 methods: getValue to get the row 0 to 1023 data, and getBrightness, which will return a byte from 0 to 255. In the implementation, the getBrightness method is the most useful. We use the Arduino map function to convert the 10-bit analog input into an 8-bit value suitable for the analog write functions we used in our LED class. This keeps the math inside the object and away from our main sketch. Now, whenever you need to know how bright the lights should be, you simply ask the potentiometer object for the brightness. If you decide later to add a smoother filter, or change the mapping range, you only need to change it inside this class, and the rest of your system will continue to work perfectly. We have all our components built and ready. In the final lecture of this project, 07.08, we will put everything together to modify the LED brightness using the potentiometer while the traffic light cycles through its states. See you in the finale. Congratulations! We have reached the final step of our project. In this lecture, we will integrate our potentiometer class with our traffic light system. We will see how the brightness value we capture from the knob is passed deep into our objects to control the physical intensity of our LEDs in real time. The magic happens in the main loop. We use the getBrightness method from our potentiometer object to get a value between 0 and 255. We then pass this directly into the traffic lights update method. This is a perfect example of how objects communicate. One provides data, and the other consumes it. Inside the traffic light class, the update method receives that brightness byte. Regardless of which state we are in, red, green, or yellow, the current LED is told to turn on with that specific brightness level. Because our LED class uses analog write, a physical light responds instantly as you turn the potentiometer. Look at this clean data flow. The hardware reading is transformed by the potentiometer class, passed through the main loop as a simple variable, and finally used by the traffic light to command the LED objects. This modularity is the essence of professional Arduino OOP. When you run this code, you'll see the lights cycling through their 5-second intervals, but you can also dim them or make them brighter at any moment. You've built a multitasking, object-oriented system that is easy to read and even easier to expand. You did it. You successfully completed the traffic light system. But this is just the beginning. In the final section, we will wrap up the course, review best practices for OOP, and discuss how you can improve this project even further. Join me in the next lecture, 08.01, for the project conclusion. See you there. We have successfully completed our traffic light system. You have built a robust, modular application using professional object-oriented principles. In this lecture, we will recap what we achieved and discuss how you can take this project even further with some advanced improvements. By organizing our code into classes, we moved away from spaghetti code. Our main loop is now just a few lines long because the traffic light and potentiometer objects handle their own complexity. This is the hallmark of a professional embedded developer. Currently, our durations like red duration are hard-coded constants. A great improvement would be to add setter methods, similar to the setRate method we built for the LED blinker. This would allow you to change the traffic flow speed based on time of day or traffic density sensors. You could also integrate the push-button class we examined earlier. By adding an express check in your state machine, you could allow a pedestrian to request a light change, making the system reactive to real-world inputs. The real power of this approach is that each of these improvements can be added without rewriting the whole project. You just add a new method or a new class and plug it in. You've proven you can build a complete system. But how do you start your next big project from scratch? In the next lecture, 08.02, we will discuss the best practices and step-by-step workflow for building any Arduino project using OOP. See you there. Now that you have built a complete system, you might wonder, how do I apply these concepts to my own future projects? In this lecture, we will distill everything we've learned into a set of best practices. These are the gold standards for building professional-grade Arduino projects using object-oriented programming. When starting a new project, don't write code in the main loop immediately. Start by identifying your hardware components. For every physical part, a sensor, a motor, or a display, create a dedicated class. This ensures that hardware-specific details, like pin modes, are isolated from your application logic. The single most important rule in professional Arduino OOP is never use delay. Instead, use the heartbeat pattern. Every class that requires timing should have an update method. By calling these update methods inside the main loop, you allow your object to check the time and act independently without ever starting the CPU. Keep your variables private. Use getters and setters to interact with them. This prevents other parts of your code from changing a pin number or a critical timing variable by mistake. By protecting your data, you make your code bug resistant and much easier to debug when things go wrong. Remember, code is read much more often than it is written. Use descriptive names like is blinking instead of flag 1. This makes your project self-documenting. Always separate your classes into .h and .cpp files. This keeps your main sketch clean and makes your classes easily portable. You can simply copy these files into your next project and reuse them instantly. This copy-paste reliability is the true reward of good OP design. Applying these best practices will transform you from a hobbyist into a software engineer. But where should you go from here? In the next lecture, 08.03, we will discuss the next steps in your learning journey and how to keep growing your skills. See you there. You have built a solid foundation in Arduino object-oriented programming. But learning doesn't stop here. In this lecture, we will explore the path forward, discussing how you can scale your knowledge to build even more complex systems and move towards professional embedded software development. Your next step is to explore advanced C++ features. Look into templates to create generic classes that work with any data type, and learn about static members to manage data that is shared across all instances of a class. These tools will help you write even more efficient and reusable code. In this course, we touched on the state machine and observer patterns. There are many more design patterns used in the industry, such as the singleton pattern for hardware resources like serial ports, or the factory pattern for creating complex objects. Understanding these will help you solve architectural problems before you even write the first line of code. The ultimate test of a good class is if it can be used by someone else. Try packaging the LED, potentiometer, or push-button classes you built here into official Arduino libraries. Add a library Dart properties file and an examples folder. Sharing your work on GitHub is a great way to contribute to the community and build your professional portfolio. The OP principles you've learned here, encapsulation, inheritance, and composition, apply to almost every modern programming language. Whether you move to ESP32, Raspberry Pi with Python, or even desktop application development with C# or Java, the logic remains the same. You are now a programmer, not just an Arduino user. The journey is far from over, but you have the tools to navigate it. Before we say goodbye, I have one last special treat for you. Join me in the next lecture, 08.04, a bonus lecture. See you there. Welcome to this bonus lecture. You have learned classes, inheritance, and composition. Now, I want to show you the crown jewel of object-oriented programming, polymorphism. We will see how to treat different objects, like a standard LED and a LED blinker, as if they were the same type, allowing us to write incredibly flexible code. Polymorphism means many shapes. In our case, it means we can treat a LED blinker as if it were a simple LED. This is possible because LED blinker inherits from LED. By using pointers to the base class, we can create a collection that holds different types of LED behaviors in one place. To make polymorphism work, we use the virtual keyword in our LED header file. This tells the compiler that when we call a method like turtle, it should check if a more specific version exists in a child class like LED blinker, and use that one instead. Inside LED blinker Dart-H, you update this line. And inside LED blinker Dart-CPP, you update this line. We can create an array of LED pointers. We point the first element to a standard LED and the second to a LED blinker. Even though they are different classes, we store them in the same LED array. When we loop through them and call turtle, the standard LED simply flips its state, while the LED blinker uses its overridden logic. This approach is extremely powerful. Imagine you have a system with 10 different types of outputs. With polymorphism, you can put them all in one list and update them with a single loop. Your main program doesn't need to know the details of each object. It just knows that they all know how to respond to the same commands. You have now seen the true scale of object-oriented programming. From simple variables to polymorphic arrays, you have the tools to build world-class Arduino software. This concludes our bonus session and our entire course. Thank you for being an amazing student. Go forth and create something incredible.
Happy coding!